Hello everybody and welcome to the video. Today we're going to be talking about the relationship between voltage and current. So I just want to give a brief recap. In the last few lessons we've learned that electricity is what happens when you separate charges and those charges want to go back to their original state. The amount of energy that it took to separate these charges is called voltage, and the rate at which these charges return back to their source is current. So if you imagine a line here, the number of charged particles going past this point per second is current. So voltage, current. But how do the charged particles go from here to here? They don't just travel through thin air, except for very special circumstances. Imagine these charged particles in something like a battery. If you leave a battery in a drawer, these charged particles aren't going anywhere. The battery will stay charged and you could use it a week, a month, or even a year later sometimes. But if you create a conductive path from the positive side to the negative side, all of a sudden, all the charged particles from one end are going to go straight to the other. Now, if this conductive path was perfectly conductive, then the charged particles would move all at once to the other side at the speed of light, just like that. And because they were separated by a difference in potential energy, all that energy would have to be lost at once, probably in an extreme amount of heat. But what happens in real life when you connect these two ends with a regular wire? Well, it's not quite as instant as that. There's still a lot of charge traveling from one side to the other, and a lot of heat escaping through these wires. But it's sort of gradual. It might take 10 seconds before the wire becomes too hot to hold. And that's because in real life, there are no perfect conductors. We can get pretty close. There are metals like copper and gold, which are almost perfectly conductive, but not entirely perfectly conductive. This is because all metals are made up of their own charged particles that all interfere with the path of the charged particles trying to get from one side of the battery to the other. The current is always going to be met with a little bit of resistance. Every single material that exists has some kind of resistance. Highly conductive metals like copper, steel, and gold have pretty much zero resistance. Not really zero resistance, but nearly zero resistance. Materials like graphite or carbon foil, they have a lot of resistance. And materials like plastic and rubber have nearly infinite resistance, which means that almost no current flows through them. In electronics, resistance is actually really useful. If you think about electronics as just controlling voltages and currents, then resistance is what we use to control currents. Resistance is so useful, in fact, that we've created an electronic component specifically for creating resistance, and they're called resistors. This is what a resistor might look like if you're a hobbyist that does electronics, or if you're looking at a circuit diagram, they're usually drawn as a zigzaggy line with a line going in and a line going out. So let's go back to this example where we have the battery and the wire. But this time, in the middle of the wire, we're going to add a resistor. Now, I want you to remember Kirchhoff's current law, which means that at any point in the circuit, the current going in must equal the current going out. This means that if we're restricting the current here, and the current coming out here is only very small, then the current going in here must also be very small. And the current coming along here must also be very small. Even if this is a perfect conductor and this is a perfect conductor, the current of the whole circuit is going to be limited by this resistor because the current going in must be the current going out. So if we do a little bit of an experiment with this resistor and we have a 1.5 volt battery, we hook up a wire to the resistor and to the other end of the battery and we measure the current going across the circuit. Perhaps we find that the current is 0.015 amps. We might say, well, if that's not many amps, our resistor is doing a good job. That's great. Now what happens if we take the same circuit, but this time, instead of using a 1.5 battery, we use a bigger battery, like one of those 9 volt batteries. We measure the current across the whole circuit, and we find that it's no longer 0.15 amps, but it's 0.09 amps or 90 milliamps. we might observe that there's more current now that there's more voltage, even though we're using the same resistor. And so you might try it again with another battery. Maybe this time you use a 5-volt battery, like the one in your iPhone. You measure the current again and you find that now it is 0.05 amps. And you realize, hey, wait a minute, I can see a pattern. The current going through the circuit is equal to the voltage of the battery divided by 100. That's true for this circuit. It's true for this circuit. 0.09 is just 9 divided by 100. And it's true for this circuit as well. The current going through the circuit is equal to whatever the voltage is divided by 100. This value, 100, is the value of our resistor. That is to say that this resistor has a resistance of 100 ohms. Ohms is the way that we measure the value of resistance, and it comes from this formula exactly. So instead of this 100, I'm going to put an R for resistance. We say that if we know the voltage, we can control the current by dividing the voltage by a known resistance R. And we can rearrange this formula here to give us the unit of resistance. So resistance is equal to voltage divided by current. We're just multiplying both sides by R and then dividing both sides by I. And that's what the unit ohms is. Ohms is just volts per amps. So when we say a resistor is 100 ohms, we're saying that the current going through this resistor is equal to the voltage across that resistor divided by 100. And this law right here, this formula, I is equal to V divided by R, or rearranged to be R is equal to V divided by I, is what is known as Ohm's law. And it is the relationship between voltage and current across any material.